Chirodambo passed away on the 5th of July of this year after having been sick for, no, I don't need this now, for about 1 year. He had a stroke in July of last year. And after that, he was absolutely, he couldn't speak, but otherwise he could in other ways communicate with people and was perfectly lucid. I mean, now well, of course, I'm certainly the person who has known him for the longest time, because we collaborated on a paper that then was recognized as fundamental, was a turning point in elementary particle physics, because the idea of spontaneous breakdown was not among the postulates of quantum field theory. Actually, the axiomatic approach to quantum field theory was very rigid. I mean, the vacuum is something which has no properties, is invariant under all transformations, and so you cannot have. Now, one must say that the idea that spontaneous symmetry breaking was relevant in particle physics, actually, the first one to speak about it was Heisenberg. Heisenberg was in the 50s, developed what was called unified field theory based on a nonlinear fermion fields, which should describe the universe. Now, this theory was very difficult and complicated because he pretended to solve also, it's not a normalizable theory, he pretended to solve too many problems at the same time. So, however, the point is that he had the wrong idea about which symmetry could be broken, spontaneously broken. He was thinking about isotopic spin, which was not a rigorous symmetry of in particle physics. But Nambu had really the important intuition. He had been working on the theory of superconductivity, and he had understood how gauge invariance, I mean, the ground state of a superconductor breaks gauge invariance. Gauge invariance, which is a symmetry of electromagnetic interactions. And what Nambu did was to understand what was the mechanism by which gauge invariance were restored in superconductivity. And he wrote a paper that, I mean, since he was a field theorist, he wrote a paper that used the language of quantum field theory. So it was something that also particle physics, physicists could read. And well, and his idea was the following. I mean, since what you get in superconductivity is that this lack of gauge invariance of the ground state is compensated by zero mass excitation, which then in superconductivity, since there is the long range Coulomb interaction, then acquires a mass, which is relevant for something which happened later with the Higgs mechanism and so on. But now, Nambu's idea was the following, that in the case of elementary particles, if you break the what is called gamma-fied invariance, chiral invariance, and that was his intuition, that was the symmetry to be considered, then you would get a pseudoscalar zero mass particle. And that should compensate the fact that the fermions have a mass, and which was forbidden by this invariance. Okay, but unfortunately, so this particle should should have been identified with the pion, and the pion has a mass. So the idea was the following: the idea that somehow the same reason by which the pion acquired a mass should be also responsible for the renormalization of the axial vector current in the beta decay, something which had been measured, and there was a positive renormalization effect on the axial current. So when I arrived in Chicago, he was playing with this idea. So we started discussing immediately, and we did a preliminary calculation, which at that time for us was very important, but was not. Today it doesn't have the same weight. Actually, it's impossible to verify. But so we calculated the simplest diagrams. I mean, it was just an exercise because it were strong interactions. The simplest Feynman diagrams which contribute to the renormalization of the axial vector, to see whether the positive mass of the pion would give a positive renormalization for the axial vector. So we did the calculation independently, and we got entirely different results, because there were a lot of divergences. So my result supported the idea. His result was against. So we discussed for a long time. I was a young postdoc at that time, so he thought that I was wrong. But then I convinced him that he was wrong. And then one day he came and he told me, "You won." And he was not too happy to admit that he made a mistake, but he was happy that the result supported his idea. So from that on, I mean, if it turned out that his calculation was the right one, we would have abandoned the project. But anyway, we agreed finally on that, and that was the beginning. And then, he started to take me seriously after that. And that actually was the beginning of a whole lifelong friendship that, he has been for me like like a father, or he was older than me, and then we developed this model, and the history afterwards is then this stimulated the Higgs papers, and also Angler, and I don't remember. Yeah, and about works. But many people were involved actually, like in this application to gauge theories. Now, so this as far as our early. Then, of course, since when I came back to Italy, I had to come back for family reasons. So, and I was very unhappy, because with Yuichiro we had established such fine-tuning, so we understood each other very quickly, and so I was very frustrated when I... well, retrospectively, I think it was not too bad for me, because I acquired an independence that probably, if I had remained in Chicago, would have been different. And anyway, I continued. I learned two basic principles from him. One, that you should never be scared by working on non-fashionable subjects. I mean, actually, since he had his son was sick at that time. The first time I was the first to present publicly this model, and I was very scared, because for elementary particle physicists that was heresy. And, but however, it was well received, and but the night before I didn't sleep. And well, okay, then there is a long story about the way spontaneous symmetry breaking penetrated. And one must say that he didn't have a name, but the first to discover, at least in some written text, spontaneous symmetry breaking was Euler in the 18th century. Because he knew the case of a bar, that if you apply some force, this for a while it contracts, but at some point it bends when the force, and this he knew. Okay, so when I came back, I tried to, our work was based on a mean field theory, and so I tried to give a general formulation, so I introduced what is now called the effective action, which then became popular. I mean, textbooks, this is the idea which is used to discuss spontaneous breakdown. And the other thing I learned from him is that analogies are a very powerful source of new ideas. And in that case was the analogy with superconductivity. And that for me was very important when with Di Castro we tried to import the field theoretical normalization group into statistical mechanics, because there were very strong formal analogies. Okay, but I want to say a few words about the last, well, with Nabu we continued to, we had, for example, in the 90s, a funny and interesting exchange on cold fusion. He was very curious about cold fusion. I had been involved in some calculation also, so we exchanged letters and mails and papers on that. But to understand what kind of person he was, I'm going beyond. Can I?
I'm very short in time. I will not take much time.
About his last years. He was interested in two things, which had nothing to do with elementary particles, but which are, one thing was based on a previous work that he had done in 1973, that was a formalism with more than one Hamiltonian. This is, it was known under the name of Nambu mechanics. Now, this idea was not really taken up by physicists, so it remained somehow isolated. And I mean, that was his feature. I mean, he had an associative mind, so you could never retrace what had been his way to an idea. And however, mathematicians had understood that this thing actually was very important, and it generated a new sector of algebra, which are called Nambu algebras. And in the last part of his life, he was interested in applying this to hydrodynamics. Now, I saw him the last time 2 years ago, and in the fall, and then we discussed also another case. But in the fall, I attended a meeting in Cambridge, where Cambridge, United Kingdom, where there were physicists of the earth sciences, which actually discovered, with my surprise, that they were using Nambu mechanics to I think independently of Nambu, because he had not published anything, to formulate hydrodynamics and to construct a very concrete calculational algorithms. So, I mean, of course, I immediately told him about that. He was very pleased. Because not only he had stimulated with that isolated paper a new sector of mathematics, but also something very concrete. And I mean, nobody had thought before of this type of of things. Really you ask, how did you think of it when you read it's an isolated paper of 1973. Yes. The other thing in which he was interested was this, there is this Titius-Bode law for the orbits of planets. And it's a kind of quantization of the orbits. It looks like a quantization. There is a simple rule for the orbits. And so he had developed, in complete isolation, an idea of introducing a quantization in some reasoning to reproduce this Titius-Bode law. Now, I had been exposed to this argument because some friends of mine have been working on it, making stochastic models like Albeverio and others. So he was not aware of this work. So when I came back, I sent him several papers, both by mathematicians and astrophysicists on this theme. And then that he read, really. He was already 92, and he was working. And so he gave, I think, his last seminar in Osaka by speaking of these two subjects, Nambu mechanics in hydrodynamics and the Titius-Bode law. And he sent me the presentation, and he had quoted all these papers. So, and he was very happy because, you see, well, when I saw him, at that time he was already sick, and he had to have dialysis 3 times a week, which was a very heavy treatment. And so he complained. And the reason why he complained, he told me, you see, I mean, in those 3 days, I cannot work. And he was 92. And so now you understand, I mean, having such an example, and the other example that we shall see in a few days is Joel Leibowitz. I mean, and now I have also reached an old age, but I cannot stop working because with these examples. Okay, thank you.
Request Spinter to say a few words.
The microphone. Oh, yeah.
For putting this session together. I think this session is mainly here because Professor Jona Lasino was visiting, and we thought that it would be wonderful to have his reminiscences of Oichiro Nambu. I'm just a bit of an add-on here because I also spent many years in the University of Chicago. And undoubtedly, he was a great physicist. I think he was one of the most important thinkers in physics in the second half of the 20th century. And the names that come to my mind, at least the people I know, because I'm from particle physics, are people like Murray Gell-Mann, who had a great admiration for Nambu, which I know personally, people like Phil Anderson, Stephen Weinberg, and so on. Gianni has already talked about the discovery of the Higgs mechanism and how it paved the way to the ideas of the standard model of particle physics. And of course, their famous work on spontaneous symmetry breaking, of how to give masses to elementary particles. He didn't mention about 2 other very important contributions of Nambu, so I will actually say a few words about that. The first is the introduction of the color quantum number in hadronic physics. I don't want to detail the history, but as you know, that there was a very serious problem of statistics and the presence of the omega minus meson. And there were very many suggestions, and Nambu and Hahn basically came up with the idea that quarks have an additional attribute, an additional quantum number like an electric charge. That solved the statistics problem. But I think what is important, he went beyond that. Beyond that in the sense that it is this charge that gives rise to a new type of electric force by which the quarks interact. And I think this is the seed of what became, in the future, in many years later, to be called quantum chromodynamics, which we know is an experimentally verified true theory of the strong interactions. The other great contribution of Nambu is string theory. There were a lot of, there was an enormous amount of work being done in order to understand the famous formula of Veneziano, of the scattering of particles, which he had proposed. And I think there are three people who basically thought that the underlying structure that leads to these type of formula is a string, extended object. I think this is a very big departure from the Newtonian paradigm of physics, in which we sort of talk of elementary laws as formulated in terms of elementary particles. But I think Nambu went one step further, and I think this is a key contribution, that he gave a law for the propagation of strings, and that law actually imbibed a lot of very symmetries, which got rid of a lot of basic problems which the string model was facing, the so-called ghost problem. So I think he was, in a sense, a great pioneer of the string model. Now, a couple of other non-physics comments. I know from, I interacted very strongly with Nambu because my office was just next door to his for 4 years. And he always used to say that whenever I got stuck, I used to revert to philosophy. Philosophy, basically he meant the discourses of Sakata and Takitani. So there's a book actually which I also have with me on philosophical writings of Sakata and Takitani. So whenever you get stuck, you should read philosophy actually and get new ideas. So that's one thing I just wanted to mention. And then the other thing was that for him, physics was without boundaries. Very effortless excursions across traditional boundaries of physics. There's no condensed matter or particle physics or nuclear physics or stuff like that. It's all one seamless body of knowledge that we are trying to sort of create and explore. So that definitely had a lot of influence on many of us, including myself. And I think one manifestation of that is the existence of this center actually, which in a sense practices science without boundaries. So I'd just like to put this point publicly, that certainly Nambu's influence on some of us who thought of creating this place is indelible. Now, just I'll end very briefly with some very personal recollections. He once told me how he arrived at the idea of the string. And I don't know whether most people in the audience may not know about what is called the KVS program in string theory, that is Kikawa, Sakita, Virasoro. After the amplitudes were presented by Veneziano and Virasoro, started the so-called dual unitarization program, how to discuss loops, higher loops in string theory. And in that appeared first time the Riemann surface actually. And Nambu said, basically, let us cut this Riemann surface and you'll see a string. So and then he also said that this somehow then reminded him very much of Yukawa's bilocal theory. So Yukawa, at some point in the early 20th century, came up with the idea of bilocal fields, fields which depend upon 2 points rather than local fields. So he said, oh, all I did was simply put lots and lots of points in between Yukawa's bilocal theory, and then you have a string field. And this is how he mentioned once, the sort of, the thought processes which arrived at this type of idea. And clearly, something personal which I'd like to say, because it really makes sense to do that now, is that when we first started working in around 1983, end of 82 in Tata Institute, in the literature appeared some very beautiful papers of Edward Witten on current algebra, anomalies, topology, and stuff like that. And at that time, we asked ourselves the question, how would Nambu actually approach this problem? So he would say that a meson field is made up of two quarks. And with that idea, actually, we then arrived at proposing the Nambu-Jona Lasino model for quantum chromodynamics, and inclusive of all the anomalous interactions which were there in the old chiral model. So we were able to derive the chiral model with anomalous interactions and all those topological ideas, simply using the fact that a meson is made up of two quarks, and you naturally arrive at the Nambu-Jona Lasino model in its form, which is relevant for QCD. So I'll just end with this, but we were all deeply influenced, all of us, myself, Shumit Das, Sriram Ramaswamy, we're all from the University of Chicago. We had offices close to each other, and clearly Nambu was an amazing, amazing influence, very mild, gentle, polite person, and we'll all miss him. Thank you.
We thank Spenta and Gianni for sharing their on the life and work of Nambu. So now we move on to the pedagogical lecture by Gianni on macroscopic fluctuation theory.
Well, now we have to be, again, we have to concentrate again on our job here. And, well, I will suffer, but I will try to use a little bit the blackboard. Now, because recently I've been, and, I presume that most of you were here yesterday, so there are some people who have arrived today, but they have heard me already many times. So I think that they can work on their own things. Otherwise, it would be very boring. So I think I can refer to the motivations I gave yesterday in the general talk, and I explained to you that we realized more recently that the path that we have been following was exactly the opposite of what, but in the same vein of what what Einstein had been doing on for equilibrium fluctuations. As you remember what I explained yesterday by quoting this more or less unknown seminar of Einstein, that he used the Boltzmann formula as a large deviation formula, and he applied it to the sphere falling in a liquid, and from this, by considering the fluctuations of the sphere in a liquid, he was able to derive the law for the Brownian motion. Going out of equilibrium, since we don't know what are the thermodynamic functionals, we follow exactly the opposite. So he combined, as I stressed, he combined his fluctuation formula with an hydrodynamic relationship. So what we shall now do is just to do the reverse. You add a noise to hydrodynamics, and a Gaussian noise, again a white noise actually, and so you let me start. Nothing happens. They're not the lights of the blackboard. Otherwise, let's keep the. Okay, so we shall discuss only diffusive systems, for which the type of hydrodynamic equations that we consider are those in which we have some conservation laws, and the simplest case in which you have one conservation. Starting from here? Yeah, that is too far. So. Okay, here you can see from everywhere. Yeah. So the equations we consider are of the form 0 plus of J of rho equal to 0. So you have a conservation law, and this current J of rho is described by a constitutive equation, so which is and it's given in the simplest case as the gradient of rho, and then you have, I guess you have a minus sign here, and then plus an external field. And this D and Chi are the transport coefficients, which these are called constitutive equations. In the general case, this rho is a set of thermodynamic variables, and you may have several conservation laws. Okay, so what is the idea? The idea is to take the current and add to it some noise. Okay, which is Gaussian noise. Actually, it's. I will write now what is the how it is defined, but and then you see from the fluctuations of a Gaussian variable that you know how to calculate the fluctuation of a Gaussian variable, you can derive so if you have a fluctuation of the current in the sense that this deviates from the one predicted by the constitutive law, and then so there will be a realization of a stochastic processes which produces it. And these fluctuations are, for example, could be thermal fluctuations or other fluctuations, and which by using, we are at the macroscopic level, by using central limit theorem arguments, we can and then you can reconstruct, and actually the form of this, if you want to define the correlation function of this in the case of in which you have you are in a bath of at some temperature T0, and so you will have some constant K. Well, this is actually Boltzmann constant in this case, T0, and you have Chi Ij. These are just space indices. I still work with, but I mean, even with one conservation law, I can be in higher dimensional space. So you have this chi of rho, and then you have delta of t minus t prime and delta of x minus x prime. Okay, so T0 is the bath temperature, is the environment temperature. Okay, and from the fluctuations of these quantities here, you can go back to the fluctuations. And simply reading this formula, you get, in fact, that we get the formula, which in this case, in this case of being at constant temperature, I can write explicitly as k T0. This is Boltzmann constant. This is the beta integral in dt for a given trajectory, integral dx of j minus j of rho, chi minus 1 of rho, and then is j minus j of rho. So you see, this is simply obtained by inverting this equation. So and that is the formula that I wrote yesterday. So you see, now this is what is called fluctuating hydrodynamics. The first to do these things was Landau, I think, in the 30s. And no, I mean, it was considering only linear hydrodynamics and simplest situations. Here we have. Now the question is, in the path that we followed in our group, we preferred not to use this approach, but to rely on models for which the large deviations could be proven essentially rigorously. The reason is the following, that when you put an expression of this kind into the equation, into the hydrodynamic equation, you get a very singular equation, an equation which has ultraviolet divergences which are worse than quantum field theory, and which presumably are totally irrelevant because we are we are interested in the macroscopic behavior. So this, now there is some beginning of a general theory of such a singular equation, but I'm afraid that even the progress is not enough to treat the case of hydrodynamics. So that's why, and the reason also that I mentioned yesterday, that in non-equilibrium you have to be very careful because it's very easy to make mistakes, and so that's why we wanted to rely on models for which every statement could be verified to at a reasonable mathematical level. Okay, now.
So this is the probability of a given trajectory, given profile. This is the probability of a given profile, is it?
Yes. Oh, yes. And as I emphasized yesterday, the fluctuation and the rho that you have to put into this equation is the one which satisfies always the continuity equation. So this must be always satisfied. So you take a trajectory given by a rho and a j, which however are connected by this. Then if I have time, maybe later or tomorrow, I will give you a different formulation. Behind this formula there is a Hamiltonian structure, and if you use it, you can write it as a kind of gauge theory, in which this constraint is actually automatically included. But I mean, this is
So if a system is in contact with two baths, like the example you were giving?
No, well, in this case, okay, you are the environment is at T0 temperature, but you have
The local temperature.
well, no, it's the temperature of the environment. Think of a vessel with a liquid, and then you have a density fluctuation, for example.
So there's a single path. There's not two paths. They're at different temperatures.
Well, in one case you have a single bath, but you may have also two baths or more baths. But the temperature is the same for all of them.
Ah.
So you have chemical potentials and electric potentials and chemical. Okay. But in fact, yesterday I wrote this formula in a more general way, in which here I put some parameter which represent the ratio of macroscopic length to a typical microscopic length, like the mean distance of molecules in a situation. Okay, so that's the idea of fluctuating hydrodynamics. And however, I mean, as I emphasized, we were interested in checking this kind of statements. Okay, so now, if you let me write again the formula that I wrote yesterday. So I will write this formula in a slightly more general way. So this is the form of the current, and one important thing that I also mentioned was the so-called Einstein relationship. So, in fact, these coefficients are related by the, well, this is the, so these are all rho dependent. And so what this relationship means is that locally, since we emphasize the local equilibrium, and actually the large non-equilibrium situation is built up by small deviations from equilibrium. So locally you have this relationship where F is the free energy density at equilibrium. So this is also called the Einstein relationship. Okay. So now, so rewriting this formula, we have that the way I wrote it yesterday was that if you want to introduce what is the empirical densities and currents, which are the density which are coarse-grained over some macroscopic volume, which now is characterized by this epsilon. And if you want this to be close to some, in some metric that I'm not specifying now, to a certain trajectory in space and time, and the large deviation estimates, it's e to the minus 1 over epsilon to the dimension of space. And then you have a certain thing that I call the, which is a function of rho and j. And this is, this will be made by two terms. One, you have, if you are, we are interested in a certain trajectories. That may be a rho or a current. We are in a, for example, in a stationary state, and some fluctuation creates some initial condition. This rho zero, and then we follow this trajectory in time. So this is t. And then this is made of two pieces. One is V of rho 0, which represent the non-equilibrium analog of free energy. And, and then you have a term which is exactly this that you obtained from this argument. So you get 1/4 of integral over dt dx of our usual formula. So it's minus j of rho chi minus 1 j minus j of rho. So this is the large deviation estimate. And as I said, the this V of rho, this functional, you have to take the minimum of, let me call this part of the, let me call it I of rho and j. So this is a functional of rho and j. So it's the inf of this I of rho and j over all j's, which such that the rho plus gradient of rho is equal to 0. And which overall, this must be all the rho which satisfies the boundary conditions. Now, why this holds? It's I will discuss it in more detail later. But you see, while the current determines the rho,
Is it with initial condition rho?
I mean, rho is the, if you want, in this scheme, is the initial condition. But you may ask, when you are in a stationary state, you may ask what is the probability of any.
Sure. No, I'm just saying that the right-hand side, you take an infimum.
Oh, yes, with the...
Over J.
No, the infimum is over J, because the point is that while J determines rho, vice versa is not true, because you can always add the zero divergence current here. Now, this variational principle can be solved exactly, and here I think I use the transparencies, because the slides, because that's maybe that's the way you find in Landau Lifshitz, the way they write the Einstein formula for equilibrium. With this, we discussed that the meaning is the minimum, and in the equilibrium case, you have you can, so it's defined by a reversible transformation, which creates the. But so this we have discussed. So this is our formula, and so let me. Okay, so let me go through two steps. First, let me derive. Here we have a formula for the joint fluctuations of current and thermodynamic variables. Now I want to find, I ask the question, what is the probability of having a certain trajectory of the thermodynamic variables, which is rho? So that's why I am minimizing all the possible currents. Okay, but let me go to an intermediate step, because I can write as a sequence of two variational principles. So Let's us introduce an external field which generates the fluctuation, the current J, according to this formula. So we introduce the external field. So the E was the already existing external field. And when we want to minimize, we want to do it the most economic way. So we want to calculate the minimum work. And then I want to show that the infimum is reached when this external field is a gradient vector field, which with a potential which satisfies, this is a Poisson equation. Because you see, you have, it's an elliptic second order equation for this external potential. So this is what, now, this we can show explicitly. So you write the external field with the gradient part and the non-gradient part. Then you do some calculations, and you see that you can rewrite this functional as this quadratic, as the sum of two quadratic forms, because the cross terms are zero. It's not immediately evident. You have to work a little bit, but this is the essence of the question. And so you see the infimum of this formula is anyway reached when this non-gradient part is equal to zero. So, and then of course, and then it's how you get this Poisson type equation. Now, going back to the density variable, you see that now you can write your functional for the density as this quadratic form. You see, this has an intuitive meaning. This tells you what measure the probability of the fluctuation is how much you deviate from hydrodynamics. Because hydrodynamics would mean this term equal to zero. So, and this is a situation typically in finite dimensional case of Wenzel and Friedlin theory of when you consider dynamical system submitted to weak noise. And here we have this operator which is defined on functions which vanish at the boundary, and you see this is the inverse of this elliptic operator. And actually, if you didn't have a space structure, this would be simply the inverse of Onsager matrix. So this is this sky as I emphasized yesterday, the same thing as Onsager matrix. But I will not discuss Onsager theory. So that is then you can.
So how is this related? So earlier you added a noise alpha. So when you were doing it kind of naively, you added a noise alpha right here.
Yes, that is one way of doing it. Yeah.
Yeah. So how is that related to it? So alpha is kind of like gradient of A, like F, is it?
No. I mean, now I have. I mean, I need the noise alpha to construct the large deviation functional, but then I discuss only the large deviation formula. I discuss everything at the macroscopic level. So you see, you have this probability, and okay, in order to get, since you see, this is exponential, there are exponentially small probabilities. So essentially, the only contribution comes from what minimizes this exponent. Now you have to think this as an estimate of a probability for macroscopic variables. So this is the usual philosophy in large deviation theory. I mean, now so that the main contribution will come from the optimal. So I want, by calculating this, I calculate the optimal current, which I need to calculate this one. So this is an intermediate step in which I derive first a dynamical functional for a rho trajectory. So rho is any thermodynamic variables. So that is the spirit. It's there is something disturbing you.
So you start from this and then find the minimum trajectory, and then that's how you get this.
Yes. So, and then you can go on. So let's, because we can even, we can even determine but that I have first to discuss time reversal. So, and I guess this is more or less the end of this argument. Of course, once you have this functional for the density fluctuations, you have you can interpret this as a Lagrangian, and then you can calculate. There is an Hamiltonian which is obtained by Legendre transformation that you can calculate explicitly, because in the time derivative it's a quadratic form, so it's trivial to calculate the Legendre transform. So you have an Hamiltonian structure associated to this functional, and these are the Hamilton equation associated. And the boundary conditions are this: the conjugate momentum must vanish at the boundary, and so you see that the hydrodynamic solution satisfies this equation with pi identically equal to 0, which is an equilibrium point for this equation. Okay, this we should somehow, this Hamiltonian structure we should remember, because we need it for discussing other problems.
1 hour.
I have still 1 hour. Okay, yeah, and so time reversal. I think this is. I'm going on now with for a while with these slides. So I want to define the time reversed process. Now, the one has to. There is not only one possible definition of time reversal. However, in the spirit of these interacting particle models, which are Markov processes, there is essentially only one natural definition. And the natural definition is this one, in which I take a symmetric interval, because then the notation are less cumbersome. That the probability of the time reversed process, called sometimes a joint process, you see, we have a trajectory in some interval of time given by rho and j. Then the probability of the time reversed trajectory in the time reversed process are determined by this identity. Okay, so you assign to the time reversed trajectories the probability in the time reversed process, which is equal to the probability in the original. So at the level of large deviations, this implies that there exists, if you call Ra the term associated to the time reversed process, then this implies this identity. However, here you have to be careful because we are, oh yes, more explicitly we have this thing. This is written for any interval. Okay, now there is an important assumption here, because a priori you don't know that the time reversed process has a hydrodynamics associated to it, and that the large deviation functional has the same structure as the original one. So this is an assumption which is entirely completely verified in the models. The models, I mean, simple exclusion, zero range, and also the what is the KMP, Kipnis-Marchioro process, and there are many other processes. These are satisfied, and so you can define a time, but this is physically is very reasonable, because what does it say? This, the idea is the following: that you think that suppose you have a situation with boundary driven and you have a current flowing, and then you want to invert this current. Then by applying suitable fields, in many cases you can do it. Well, if it is an electric due to an electric current due to a field E, then if you apply a field minus 2E, you get the inversion of the current. And or otherwise, by acting on a system, by doing some work, you can have heat going from low temperature to transfer heat from low temperature to higher temperature. So physically, it's a very reasonable assumption that the time reversed process, which in particular inverts the macroscopic current, so that the time reversed process has the same structure. So, but then at this point, I think you, I don't know whether I have it in this. Okay, so now you assume that for the time reversed process, you have also a functional exactly of the same form, where this is the current associated to the time reversed hydrodynamics, and then we shall see exactly what they are. Now, then I will identify also the optimal trajectory, which defines this relationship here. But first, let me draw some general consequences from the time reversal. So from the identity that I just wrote before, from here, let me draw some consequence of this identity here. Clearly, the V is the same, because the process and this time reversed have the same invariant measure. So the V is the large deviation, the static large deviation functional, or the non-equilibrium free energy is the same for both processes. But what is changes is the dynamic part. And so, okay, so how do you do? So let's take a symmetric interval, so things are simpler. Then you divide both sides of the previous identity by twice the time, and then you let the interval go to 0. And then you get this relationship written here. That is a trivial step, you see, which is an equation which contains both rho, the different j given by the constitutive equations, and also by so the fluctuations rho and j. So, but now everything is at one instant of time. So, and this has to be satisfied for any choice of rho and for any current and thermodynamic variable. So if you explicit this condition, you immediately see that you get two identities have to be satisfied. One is that the current and the current associated to the time reversed process are related by this large deviation functional, by this statical large deviation functional. You see, this is what, even in equilibrium, this V is the equilibrium entropy or free energy, and this is what even in Onsager theory is called the thermodynamic force, because this quantity must be zero on the stationary state. And the other equation, so this you see is a kind of fluctuation dissipation relationship for the currents. Actually, this for the current, I've never seen it written before for the currents, but and it's very general, and you begin to see the important role that this potential or quasi-potential, as it is called, plays in this situation. And the other relationship, you see, it tells you that the dissipation associated to J rho is the same as the dissipation associated to the J of the time reversed process. So when the time reversed process relaxes, it dissipates for unit of time. Here there is no time, so it's a dissipation for unit of time. And clearly these equations are entirely symmetric in the two variables. And now I introduce...
J-star saying the J in the previous slide.
J-star. First line.
Oh, sorry, that is a mistake. I mean, it's JA. Not clearly, I mean, it's a misprint. Now I define, I split the current in two terms, which are have opposite transformation properties under time reversal. And that is an entirely general thing that you can do for this. You see, this, so I define what I call a symmetric current, and then we shall see why, which is minus chi and minus chi the thermodynamic force. Let's call it the gradient of this derivative, the thermodynamic force. Now, this is a current, a part of, I call this current is clearly zero at the stationary density, rho bar, which is a minimum for this functional. So, and so dV over d rho is equal to 0. So this symmetric current vanishes on the stationary profile. Now I write the hydrodynamic current, which I know is this total, by writing in a part which I call the anti-asymmetric part, the anti-symmetric current, which is defined by difference, by the difference of this. Then you see that on the stationary state, where this is 0, the total current coincides with the antisymmetric part. And the antisymmetric part is the part of the current which provides the dissipation for keeping the system out of equilibrium.
Sorry, I'm confused. In your fluctuation dissipation relation, That implies this J subscript A is the same as J superscript little a, no? I mean, because this is precisely the right-hand side of the first equation of 22. So
Yeah.
J plus JA equals J symmetric.
Yeah.
So
No, but I mean, if you are in a stationary state, the right-hand side is 0.
Okay.
Okay? So it tells you that JA is minus. I mean, because in the time reversed process, the current flows in the opposite direction.
No, I'm just asking, is J superscript A the same as J subscript A of the next slide? Because
only on the stationary state. Only on the stationary state.
Okay.
Because the right-hand side is 0.
Okay.
Yeah. So you can rewrite the hydrodynamic current as the sum of these two pieces, and then you you realize immediately that you can rewrite these two equations, these two consequences of time reversal, which were the equation 22, in fact. You can rewrite these two equations in terms of these new objects, which are JS and JA. Okay, and then you see, well, that the current associated to the time reversed hydrodynamics, the JS term is the same, and then you subtract the JA term. And the second relationship is an orthogonality relationship between the two currents. So these two currents are orthogonal under space integration. So there are two orthogonal vectors. And now suppose you, let's go back to the equation 22. Now, suppose you insert the first equation into the second one. So you insert, the place of GA, you insert what you get from the previous equation. Then what you get is this relationship. But this is exactly the Hamilton-Jacobi equation. So here I don't refer to the variational principle. It's by introducing this general splitting induced by time reversal of the current, I find that the orthogonality of the two types of current give rise, it can be rewritten as a Hamilton-Jacobi equation. They express exactly the same thing. You see, this splitting is physical because once you are if you are, for example, in equilibrium and you relax to the equilibrium state, then you have only the JS current. The JA, the antisymmetric part is missing. And on the other hand, if you are in a stationary non-equilibrium state, the JS current is 0, and the JA current is what provides the dissipation to keep the system out of equilibrium. Then in intermediate other cases, they are mixed. And I think this splitting is one of the main consequences. So you see, you can write the equation for the hydrodynamics, you can write it in this way, and for the time-reversed hydrodynamics can be written in this way. In equilibrium, these two terms are missing. This is the antisymmetric part, as you see, and this is the these terms you have also in Onsager theory. In near equilibrium theory, this is represent what is called the thermodynamic force. Now, you can write explicitly the time-reversed hydrodynamics, and also, so you see that the time-reversed hydrodynamics, here you have you have to modify the external field by adding twice the thermodynamic force, and this is this looks like now it doesn't look like a well-posed problem because the Laplacian has changed sign, but actually if you develop this expression, you get from this part here, you get and using the Einstein relationship, you get this is also a relaxation equation. Okay. Now, you can also identify the optimal trajectory, which defines your non-equilibrium free energy. So the optimal trajectory, which satisfies this principle here. And okay, so, sorry. No. Okay, so suppose you start at time minus infinity in a stationary state, and you want to know what is the probability that at time zero you get a fluctuation rho. So now if you look at this expression, well, this is the identity. You see, so let's say we start at, so let's take T1, or you can take a finite time and then go to a plus infinity, but let's take T1 equal to minus infinity, for example. Then this term is 0, is missing. Then you have this, for example, this you take T2 equal to 0. And then you see that if you want to optimize this quantity I, so to find its minimum, this term doesn't depend on the trajectory. So this is a positive quantity. You have to make this quantity vanish. You see, this is a relationship among positive quantities. So this one, is I start from a stationary state, is 0. Because okay. So then you see, what I want to do is to minimize over all the currents in this expression here. This is my variational principle. So let's minimize. This doesn't depend on the trajectory because this is fixed. So the best you can do is to make this quantity vanish. So you learn that the minimizer is defined by this equation. So you must take the time reversed hydrodynamics, then you must take, so that, for example, you have, so and then it tells you that the time reversal of this trajectory must be a solution of the time reversal hydrodynamics. Well, let's see, let's make a picture. Then I give you a okay, let's first consider the case of equilibrium. In equilibrium, the time reversal hydrodynamics coincides with the original one. Okay, so this tells, suppose you have a relaxation trajectory. So here is rho as a function of time. So this rho, then you let the system free and then it relaxes. Then this equation here tells you that you have to take this relaxation trajectory and go the other way. So this goes down. And so this tells you that the time reversal of this trajectory is a solution of hydrodynamics. So this identifies completely. But in the non-equilibrium case, these two trajectories will be entirely different. The trajectory which creates the fluctuation. Now, there was an interesting simulation that was done in England by Luczynski and McClintock. They considered that this Langevin type equation with where f is in 2 dimensions, and this is a non-gradient system. So this is what in Langevin equation simulates the non-equilibrium. So this is okay, and they made an experiment. They constructed with electronic devices, also with with random. They constructed a random generator and so on. So they constructed an analogical computer to simulate this equation. And then you see, they found that one of the, I don't remember whether the blue ones or the red ones, I think the blue ones are it's the relaxation trajectory, and the red ones are those which create the trajectory. They did not understand why. So their article, which is in Nature, they were very surprised, and this comes out also from the calculation that the minimizing trajectory has to be different from the relaxation. But they didn't have the notion of time reversal diffusion. So, but now we understand what it is. The trajectories which create the fluctuation are related to the time reversal hydrodynamics and not to the original one. Okay, so and these were people who are very. They did calculation with a lot of work with the Langevin equation. So they didn't follow actually what was happening in non-equilibrium. So when I told them, they were surprised, but they were quite happy. Yeah, I told them, your paper has now become very popular. Yes.
I have a question. So since you have an explicit form for I of rho,
yes,
and you have time reversals,
yeah,
let's assume time reversal symmetry, then you should have an explicit form for IA of rho also, right? I mean, it should be quantitatively different from I rho when you start from non-equilibrium, from a non-equilibrium system.
No, but
system out of equilibrium.
I mean, what you mean?
So you have this form for I rho j, right, which is this integral over.
Yes, yes. No, but you see, the form of I, okay, from what I said before, the form of I A of rho and j will be exactly the same thing. So, so there will be dt, dx, and then you will have j minus ga of rho, chi minus 1, well, so it will have exactly the same expression, but with j, with ja, which substitutes.
And rho will be the same.
Yeah. And again, they must the rho must satisfy the continuity equation. So then you can also do a simple calculation. You can write the quasi-potential as the the integral of its time derivative. Here the meaning of rho star is that is the optimal trajectory. So this rho star has nothing to do with time reversal. It's the optimal trajectory. It is not written that. And then you simply do some integration by parts and so on. And then you realize that it is exactly the work done by the thermodynamic force, which is you see, the thermodynamic force is the gradient of dV over d rho. And then you see by this expression that this is exactly the work done by this force. And this comes out with the correct 1/4 factor. I mean.
This is the work done in the adjoint hydrodynamics? Is this the work done in the hydrodynamics or the?
Yes. It's the work done by hydrodynamics. Yeah. Or it's the work that you have to do, to create the fluctuation, or it's the work that you can get from the system by relaxing, by having the fluctuation relax. So can I go on? Yeah. Now, just to give a trivial example of the splitting of the currents, let me just take, for example, this is a typical expression that you find in some solid-state books like Mermin and Wagner. Suppose you have an electron and you see, and they have a magnetic field, okay? So you will have, since the electron in a medium it has some friction, so you will have a relaxation term, and then you have the Lorentz force term which acts on it. So it is the charge, H the magnetic field, and so on. Then you see that in this simple example, the Lorentz force is exactly orthogonal to the dissipative part. And so this is a trivial example of that splitting. In this case, then if you define time reversal by sending p to minus p, 8 into minus h, and then the adjoint equation coincides with the time reversal equation, and you get exactly that this part here changes sign, while this part retains a sign. And in this simple example, these are the definition of GS and GA. Then a gas of independent particle also, so it's a special case of the zero range process. And you can calculate very easily what are the JS and JA and verify the orthogonality. Or also in the case of a circulation of fluid in a ring. Well, this requires something that I will say later, I guess. So this is a general principle that you can, once you have the non-equilibrium free energy, you can split the current in two parts which are orthogonal and which have opposite transformation properties on their time reversal. Well, that maybe I can skip, but I mean that you see, you can have a dual formulation of this variational principle, in which instead of minimizing with respect to the thermodynamic variables, you minimize with respect to external field, which create the fluctuation, and then you get a control type problem. So now let's discuss some cases where our quasi-potential or non-equilibrium. Well, first of all, this theory includes the equilibrium states. So in equilibrium, you can calculate, I mean, if you know the density of the equilibrium current, but you have also the part which comes from the interaction with the reservoirs, then you can see immediately that this is the explicit expression. So this is the explicit expression of the density, of the equilibrium density when you are in contact with the reservoirs. So you have this part which depends on the thermodynamic force, and then you can verify that the integral of this expression here, in fact, verifies the Hamilton-Jacobi equation. You have to use the Einstein relationship in order to prove that, in fact, satisfies the Hamilton-Jacobi equation. And now I can define what is macroscopic reversibility. I will define macroscopic reversibility. This is, I think, is a relevant concept because it's a concept that is independent of what happens at the microscopic level. Because when you go to from the microscopic level to the macroscopic level, you lose information. So, for example, if you have, on that we had produced examples with Claudio Landim and Davide Gabrielli in the 90s, because if you have violation of the detailed balance on a small scale, this is, when you go to the macroscopic level, you lose it, you don't see it. So it doesn't influence hydrodynamics. That is the point. So it's natural to define macroscopic reversibility when J rho is equal to GA of rho. So this I will call, I guess is what it's written here. So you see, this relationship is what we got from time reversal. And then, so if you extract the JA, this is given by this term minus the original current. And this is what we call macroscopic reversibility. And then these you can do as exercises. They are in our papers, but it's really exercises to show that if in a stationary state you have zero, so if in a rho bar, the stationary state, you have zero current, so it's an equilibrium state, this is entirely equivalent to macroscopic reversibility. You can prove in one direction and the opposite direction. So everything is consistent. And then you realize that the construction of V when you have macroscopic reversibility is much simpler, because now you have that J rho, I mean, if you have this relationship, now J rho is given simply by this expression. So you have only one integration to do to recover the V. So you don't have to solve the Hamilton-Jacobi equation. You have only to use this relationship. And then also there is a nice remark that suppose that V is a non-local functional. But still you have reversibility. This happens, for example, in the so-called ABC model, in which you have a situation in which is like equilibrium, And but the model is not time reversal invariant because you have a rotation in this model, and so long-range correlation are allowed. No locality is allowed, and then since the hydrodynamics from which you started is local, this implies that also the thermodynamic force must be local from this relationship.
Okay. Macroscopic reversibility seems like a very strong condition, no? I mean.
Well, but it's you can give many examples. I mean.
But local detail balance violation, but no global.
Exactly. You can give examples both in case of conservation laws and examples in when you have reaction diffusion systems. In both cases, you can give. Actually, I mean, that was a paper that we wrote with Claudio Landim and Davide Gabrielli in the middle 90s. But just we took the zero range process, and which didn't satisfy the detailed balance. So at the microscopic level, but only in such a way that at the macroscopic level you would not see it, and so this you have a whole family of models which satisfy this macroscopic reversibility.
So you expect such systems to be diffusive? Or diffusive? You think diffusive systems?
Yeah, I mean, for the moment, the theory developed refers to diffusive systems.
But there you expect all systems to satisfy, or generic systems to satisfy?
I mean, yeah, I mean, if you have systems, for example, with a zero range process, you can construct a whole family of microscopic models which have the same hydrodynamics and satisfy this macroscopic reversibility. Now this I will skip completely. A microscopic derivation of the, but you find so let me give. Yesterday I said that there is one case, non-trivial, in which you can calculate and this is the boundary-driven simple exclusion. And the first time it was calculated by Derrida, Leibowitz, and Speer, and then we calculated by different solving the Hamilton-Jacobi equation, and so we could understand what was this mysterious equation that they had found. And in fact, we published our papers in the same issue together, so you had the two versions. So you see, the Hamilton-Jacobi equation for the boundary-driven without external fields, you have only conditions at the boundaries. This is, you see, is the mobility for the simple exclusion, rho 1 minus rho. And the diffusion coefficient is 1, so it gets this simpler form. Now, how can you reduce this to an ordinary differential equations? So let me. So what appears in this equation is the derivative of this quasi-potential, or this non-equilibrium free energy. Let us split. So let us write it as the equilibrium part, which is this one. So this is the equilibrium part for the simple exclusion, plus a term, okay? And then you can see that this function phi has to satisfy these boundary conditions, because this the derivative must vanish at the boundaries. This is not completely evident, but there is an argument showing that this is the case. Okay, then if you insert the previous expression in the Hamilton-Jacobi equation, so you see that you can rewrite the Hamilton-Jacobi equation in this form. Okay. No, I mean, yes, if you want. You have this integral condition. Then, okay, you add and subtract this expression. Sometimes I use capital phi and sometimes lowercase phi. I mean, that's, you know, when you write slides. So, by adding and subtracting this expression, you can rewrite the previous, the right-hand side of the previous identity in this way, and use the fact that this difference due to the boundary condition vanishes at the boundary. And then by doing some integration by parts, finally the Hamilton-Jacobi equation reduces to this expression here. So this is is a scalar product of two factors. So, but one possibility to satisfy this one is to have this right-hand side vanishing. I mean, you could also have this vanishing, but that you will get a trivial solution. So, but if you have this part vanishing, you get exactly the Derrida Leibowitz and Sperr equation, which expresses this phi as a non-local function of the density. And now you have to prove that this is the maximal solution, so it's the one in which you are interested. But this can be done. So yeah, there are a certain number of non-trivial verifications that have to be done, but in the end, you see that in this case, the Hamilton-Jacobi equation is reduced exactly to the Derrida Leibowitz and Sperr equation. And so then once you have this phi, you can calculate explicitly, explicitly modulo solving this equation. You can call the quasi-potential, and then you see that this, since this is a highly non-local function of the fluctuation, this you have assigned, then this part is non-local, and this is the equilibrium part. This part is non-local, and you have long-range correlations. So,
10 minutes.
Yes. No, I have much more material, but we shall see at the end of tomorrow at which point we have arrived. But then you will, there is this review which contains almost everything, almost. There is an additional paper which has just come out in the Journal of Statistical Mechanics. But I want to say something about that. So you see, you realize that you can define, if you take the Legendre transform of your non-equilibrium free energy, you get the generating functional for correlation functions in the stationary state. So you can rewrite the Hamilton-Jacobi equation by making this change of variables. So you can take as independent variable the derivative of V, and then the rho is replaced by the derivative of G. So the Hamilton-Jacobi equation takes this form, and then you expand it. You expand it, you define these are horrible equations. So, there is horrible combinatorics. Only the two two-point correlation. But anyway, the correlation functions in a stationary state are defined by the functional derivative with respect to h variables. Then you can write a system of equations, of recursive equations, to calculate them. But the interesting case is now let me discuss the two-point. The two-point equation you see, at equilibrium you don't have long-range correlation. So the equilibrium part is this part here. It's just the variance, which is calculated in the stationary state. And so you have here a delta function you don't have. But here now you have, for example, in the simple exclusion process, this is the non-local part. And then you take the previous equation and you find a simple equation for this part B, where L is an elliptic operator, is a formal adjoint of this elliptic operator, which contains in the general case it contains this matrix, the diffusion matrix, or this the derivative of this mobility. So introduce this quantity alpha, and this quantity alpha is exactly what appears here. So you see, if this alpha is different from 0, you get long-range correlation. But if this alpha is 0, then you don't have. Now, this alpha contains various things. It contains the stationary current, which is divergent free, and then it contains the derivative of the mobility. Then you see immediately that you get long-range correlation. To get long-range correlations, you need some nonlinearity, because otherwise all the interesting effects are connected with. Because, for example, I mean, if you have a constant mobility, this factor is 0. And that is the case of the Ginsburg-Landau model, for example. So in this case, but in the simple exclusion case, the derivative and also the second derivative of the mobility is different from 0. And now, in the simple exclusion case, this D is equal to, is a diagonal matrix and constant, but this part contributes to it. Now, we have not been able to understand completely what is the physical meaning of having this derivative of the mobility different from 0. That is somewhat mysterious. I discussed it once also with Varadan, but he didn't have an explanation. And so here there is some problem of physical interpretation, which may be interesting. To understand why you need, for example, if you have constant diffusions, what is the meaning of having the derivative of the mobility different from 0? And this is a physical question. Okay. So the non-equilibrium long-range fluctuation have been measured actually long ago in the beginning of the 90s, and you see that if you didn't have long-range correlation, you would get some flat. And here you clearly you have some non-trivial dependence. Well, these quantities are, this K dependence is associated with the form factor of experiments in which you do the scattering of light and so on and so forth. I mean, and it's interesting that this macroscopic fluctuation theory predicts generically that you have long-range correlation. Because this long-range correlation have been predicted starting from kinetic theory. But they were really very difficult papers to read. And in fact, one of the authors once told me, don't read those papers because you don't understand anything. But here it's very simple, the way you get long-range correlation. So that is one of the well, that I may add this. When you have, for example, you have a ring, and then you put the system in motion with an external field, and the external field is constant, then everything is like in equilibrium. That you can understand because you can go to a reference system moving with the current, and there the system is in equilibrium. That you can verify explicitly that if you add a constant field, the Hamilton-Jacobi equation is satisfied anyway. No, I think that is a good point to stop. Or I am through. Yeah, okay.
Okay, so if there are no questions, we'll break for the coffee break, and we meet at 11:50.